All right, at first glance, this is the same problem as the last one. But this problem asks us for how fast the mass is moving when it has moved 10 centimeters from its original compressed position. So it's actually asking us for the speed at a different moment in time. So I'm going to go ahead and draw in a rough sketch. Here's my equilibrium. Oh dear. Sorry, I don't know what I just did there. So again, we have our mass pushed against the spring such that the spring is initially compressed 25 centimeters. So that part is the same. The difference is it wants to know how fast is this mass moving when it has moved 10 centimeters. So when it's gone this way 10 centimeters from its original compressed position. Sorry, that's a terrible spring. Not much better, but that's okay. So we want to know this speed right now. I'm going to call that V final simply because I know initially I compressed the spring 25 centimeters. Final, I want to be the moment at which I'm trying to find this final speed. So the spring here is still compressed. So S final, well, if it was initially 25 centimeters and we are saying that the mass has now moved 10 centimeters, S final will be 15 centimeters. So I find it very helpful, as you've probably noticed all along, draw a rough sketch so that we can accurately account for distances, positions, all that good stuff. We're going to use net work is equal to the change in kinetic energy again. And by net work, we mean the work done by the normal force, work done by the spring, work done by the force of gravity. So we mean the work done by all of the forces acting during this motion. But the normal force and the work and gravity are not doing work simply because they are perpendicular to the motion. So the net work done is the work done by the spring, which we've already calculated the work done, work done by a spring, negative 1/2 K S final squared, or delta S final squared, plus 1/2 K delta S initial squared. Again, I don't like to write the deltas. We already have enough variables in here. So that's partly why I draw my picture, is because the S in the work equation needs to represent the compression or stretching of the spring, how far it is moved from equilibrium. So that's why I draw it from equilibrium. V initial is still going to be 0, because we just push the mass to the side and release it. But this time we do have an S initial and an S final. So we can't take one of those to 0. We can cancel out the 1/2. So on the left, if I want to factor out a K, I would have minus S final squared plus S initial squared. I will need to divide by mass. This will equal V final squared. So I will need to take the square root of both sides. Now, just total side note, S final squared, S initial squared is not the same thing as minus S final plus S initial squared. Okay, do not do that. I've seen that before. It's a common mistake, so that's why I want to mention it. All right, so K 200 newtons per meter, mass 5 kilograms. S final is our 0.15 meters, and that in here is what's squared. The negative sign is not part of the term that is squared, so we do end up subtracting this piece. And then 0.25 squared throwing our numbers in. .265, so 1.3 meters per second. If you happen to go through the last video, this is slower, which should be expected because the spring has not done the maximum amount of work that it possibly can. And so the mass has not sped up as much as it will. So equilibrium is where the mass will be traveling the fastest, simply because the spring will have done the most amount of work by the time it gets there.